Okay, good afternoon, everybody. Our presentation is Earth Dams. My name is Jessie Johnson.
Jackie Galen. I'm Andrea Dotolo.
I'm Alex.
I'm Zach Ferguson.
Mike Sistai.
Nate Coombs.
Great. So let's get started. Earth dams are one of the oldest types, or it is the oldest type of dam, dating back to like 2700 BCE. It's constructed from natural materials like soil, clay, and rock. It's built to retain water and to harvest water for irrigation purposes, recreation purposes. Also, you can use it for hydroelectric power, etc. Its simplicity of construction and maintenance makes it a desirable option for dams, and it is normally built over wide valleys on hard rock or on softer soils, depending on pore water pressure. The dam basics, so it's basically an earthen embankment that's preventing the flow of water, and its shape is what gives it its strength as well as its weight. Most dams have an impervious core in the center, which prevents the seepage of water through the dam and out the other side, and the layers of the material provide a path for drainage if the water gets to a certain level.
When building an earth dam, some things you should consider during construction are compaction, the selection of the fill materials, and the impervious core depth and material selection. Earth dams are made up of all earth soils. Coarse soils are used for their internal strength, and fine soils are used more for barrier against water. And broader graded materials are used for hydraulic conductivity, low compressibility, and shear strength. Some specifications. When you're designing the height of an earth dam, it's pretty obvious that the height just has to be high enough so that water doesn't overtop the dam, even during storm conditions and with high waves. And the width is dependent, or the minimum width is dependent on the height, which can be found from the table below.
So one of the biggest problems with these dams is that they often fail, and that's either due usually to overtopping, seepage, or a structural failure. Overtopping is the result of water erosing the top of the dam, and these earth dams are typically not designed to be overtopped. So once it begins, it's almost impossible to stop. However, if the dam is well vegetated, it might withstand some overtopping. Seepage is controlled by the velocity and quantity that water's going at the dam. It's what we've learned in class many times, how the water flows through the soil. It usually begins on the downstream side of the embankment, either in the dam proper or in the foundation, and it progressively works towards the reservoir and eventually develops pipes. And piping action can be recognized by an increased seepage flow. This picture is an example of a piping failure where the water just started to come through, and it eventually causes this structural failure where you see slides. Noticing failures such as piping where water is coming through the other side of the dam, where you see an increase in seepage, is a very good indication to warn someone that a problem is about to occur. Also, if you see a whirlpool on the other side of the dam where the water is, it's likely that your dam is about to completely fail in a matter of minutes. And these all just cause structural failures and can be noticed, it's cracking, settlement, or slides.
So our first case study, we looked at the Mount Poly mine. It failed in August 4th, 2014. The main perimeter embankment wall that was retaining the water plus all of the waste slurry from mining released into the surrounding reservoir, and this image shows the overall site of the plan. A total of 10 million cubic meters of water was released, and 4.5 million cubic meters of slurry were released first into the lower lake. Next slide. And as you can see, once it reached the lower lake, it raised it a total of almost 5 feet and flooded the next biggest, deepest freshwater lake in Canada. And this was all caused by a failure in the dam foundation materials. The geotech survey that was done at the beginning of the project included some mapping and surveying, but it did not find or account for the glaciostine or GLU soil layer that comes in when the glaciers melt, and reform, depositing more and more soil. If this had been noticed, the dam could have been built properly and not failed.
Okay, so the second case study that we looked into was the Teton Dam, which is one of the biggest failures of dams that's been seen. As you can see down here, there's a lot of water coming out. But the original design for the dam was over 10 million cubic yards of fill that was brought from the bed of the reservoir area and brought up. And then the center of the dam was a mixture of clay, silt, gravel, and cobbles tightly compacted to be considered impermeable. And then the outside layers were just various types of rock material. And it was designed, the foundation was designed with 4 elements, which were the key trenches on the abutments, cut-off trench to rock, continuous grout curtain along the entire foundation, and the excavation of rocks under the abutment. And then the embankment had its own design that was also broken into 5 zones, similar to what Jesse showed on the original slide for a general design of Earth Dam. And just stay there. And so this began to fail. It was 2 days before the entire thing burst that they started to see seepage problems right near the abutment wall. And then the next day, they were seeing small springs coming out through piping, and it started really having a huge flow at 7:30 in the morning, and then by 11:30, it had completely busted open, and all the water rushed out, and 2 excavators were trying to stop this by pushing in riprap, but they fell. They got swept into the whirlpool and got swallowed up into the dam. And because of this, 14 people were killed, and there was over $1 billion in property damage. And the reasons for the failure were due to 2 different reasons: geological and design failures. The geological design was that the area was rich in volcanic rock, so it had very many joints, and it was highly permeable, which allowed the water to just travel through the foundation of it. And also the soil that was used for the fill was highly erodible, which was not a good idea to do. And for the design, what failed was that the grout that was used in the grout curtain is most likely going to fail just by the way that the design is, but they did not account for the failure for when it does fail, they didn't account for anything to fix it.
Hi, room 258. This is the circulation desk. We just wanted to let you know we have a group down here waiting for the key. If you could return it as soon as possible, we'd really appreciate it. Thanks.
So that allowed the piping to occur and the water to start coming out on the other side. And then the geometry of the dam in general created areas of high and low stress, which made cracks favorable. And also at compaction, the soil was compacted, it was not at optimum moisture content to get the maximum dry density. And then this is just a picture of where it was failed, where all this was wiped out, and yeah, this is all like the flood debris that's showing, and that's all that was left of it, and this is just a general schematic. And Zone 1 is where the failure occurred, which was supposed to be the impermeable layer, but it was not because the soil wasn't used correctly and it was able to be eroded. And then the lessons learned, there was 3 aspects that were looked into. there's more investigation of geology on the site now that needs to be observed to make sure that it has the right geological characteristics to build a dam. The professional procedural aspects were that they just need to do more peer editing and more frequent visits from design engineers and do more redundant seepage controls to prevent piping. And because of this, also the dam safety program was created. And then the educational importance was just, educational aspects was just the importance of engineering, geology, and geotechnical engineering for students, for them to learn about stuff like this in class before getting their degree and becoming engineers.
For case study number 3, we looked at the Cham Dam located in Nigeria. This dam was in service for only 6 years before it failed. Failed as a result of inadequate research and planning, inconsistent design, and failure for the construction crews to adhere to design. In Africa, earth dams are most common. They're prone to drought, so there's increased importance in this dam building. The Cham Dam provided water for irrigation, drinking, is served for flood protection, and as a source of water for animals. In the planning process, there's almost no research done regarding the geology, hydrology, drainage, or topography. The design plans were inconsistent. They had numbers that they used for flow rates and just no references where these numbers came from. The construction crews, they commissioned the dam without ever completing the spillway. The crest was never reached the desired height, and the improper materials were used. The dam failed eventually as a result of overtopping and seepage combined, and then it just failed entirely, as you can see here, picture. And that's it.
All right, so just as a recap of what we've talked about, these dams are basically made of soil, sands, clays, and rocks, more or less semi-plastic components, and these dams also include central impervious core to prevent seepage, which is the main cause of failure, and multiple failure modes are also seen here as seepage, erosion, and structural considerations. Any questions?
Okay, sorry, we're coming down right now.